Hello and welcome. Today we are going to pull back the curtain on the hidden architecture that basically powers our entire connected lives. We're diving into the complex, brilliant, and absolutely essential world of distributed systems.
I mean, really think about it for a second. Billions of us are online right now, streaming, banking, communicating, all at the exact same time. How is it possible that this massive global system just stays afloat? It's not magic, but, it's pretty close. It is an absolute marvel of engineering.
Well, the secret lies in these invisible blueprints. These are the master plans, the models that architects use to design systems that are powerful, resilient, and can operate on a global scale. And today, we're going to walk through those blueprints together. We're going to start with the big picture, what I'm calling the city plan, which is all about how the physical computers are laid out. Then we'll zoom right into the building plan to see how the software itself is structured. After that, we'll get down to the nitty-gritty, the laws of physics, the fundamental rules that govern everything. And finally, we'll wrap it all up and see why any of this matters to you.
First up, the city plan. So this is our highest level view, our 30,000-foot view. We're looking at how we arrange the actual hardware, the computers themselves, to work together in a distributed system.
Let's start with an early blueprint, the mini-computer model. This was really just an extension of the classic centralized mainframe systems. So the idea is you have several powerful mini-computers, each one serving multiple users, and they're all interconnected so they can share resources like files and printers. In fact, the early ARPANET, the precursor to the internet, was a prime example of this model in action.
The setup is pretty straightforward. You've got user terminals that connect to their local mini-computer, but the real magic is the central communication network. This network lets a user on one machine seamlessly access resources, say a specific data set or a printer, that's located on any other machine in the entire system.
Okay, now let's switch gears to a different idea. By the time workstations, those powerful personal computers, became common, a whole new problem popped up. You had all these powerful machines, but a lot of the time they were just sitting there, idle, wasting a huge amount of processing power. The workstation model was designed to solve exactly that.
So here's the city plan for that model. You've got a collection of workstations, one for each user, all connected by a high-speed local network. The core idea is all about resource sharing. If your machine is bogged down with some heavy task, the system can go find an idle computer somewhere else on the network and borrow its CPU to get your job done way faster.
Now, within this workstation world, two main approaches came about. The diskful approach gave each computer its own hard drive and operating system. Simple, right? But it created some major management headaches. So, the more advanced diskless approach, which is part of the workstation server model, had workstations boot from and store files on a central, powerful server. It was a bit more complex to set up, sure, but it was way more efficient for system administrators to manage, maintain, and back everything up.
Two more advanced blueprints also popped up. The processor pool model completely does away with the idea of having your own personal home machine. Just imagine a huge rack of CPUs that any user can tap into whenever they need it. You just request the processing power you need right when you need it. And then there's the hybrid model, which combines the best of both worlds. You get a personal workstation for all your everyday interactive tasks, but you can also access that shared processor pool for the really intensive jobs, like rendering a 3D model or running a complex simulation.
All right, so we've laid out our city of hardware. Now let's zoom into the building plan. At this level, we're not talking about the physical machines anymore. This is all about how we structure the software components that actually run on them.
In academic terms, an architectural model defines the system based on its components, those are the individual pieces of software, and the connectors that create the communication pathways between them. It really just answers two key questions: what's each component responsible for, and how do they talk to each other across the network?
So the most famous software architecture has got to be client-server. And it's just beautifully simple. Think of yourself as a client in a diner. You send a request, your order, to the server. The server does the work, it makes your food, and then it returns a result. This whole conversation follows a defined set of rules, or a protocol. And this simple request-reply dance is the foundation for a huge chunk of the internet.
The client-server is just one style. In layered architectures, components are stacked, with requests flowing down and responses flowing up, kind of like how networking protocols work. Object-based architectures treat every component as its own independent object, communicating with others. Then you have data-centered models, which is super common in businesses, and they place a shared database at the very heart of the system. And finally, event-based architectures use a publish-subscribe model, which we'll look at right now.
Okay, let's zoom in on that last one. In an event-based system, components don't talk to each other directly. Instead, one component publishes an event, like, hey, a new user signed up, to a shared event bus. Then, other interested components can subscribe to that event and react whenever it happens. This creates what we call a loosely coupled system. And it's incredibly flexible because you can add, remove, or change components without breaking all the connections between everything else. It's really powerful.
Okay, we have our city plan for the hardware and our building plan for the software. Now we have to dig down to the most abstract level, the fundamental rules that govern any distributed system, no matter how it's built. These are kind of like the laws of physics for our digital world.
These fundamental models force us, as designers, to answer three critical questions. How do processes interact with each other across a network? How do they fail? And how do we protect them from an attack? The answers to these questions really define the environment our system is going to operate in.
Let's start with interaction. Here we really have two opposing views of the universe. In a synchronous system, you can set hard limits on everything: how long a process takes to run, how long a message takes to arrive. This makes the system super predictable, which is great for certain applications, but it's very difficult and expensive to build. On the other hand, you've got an asynchronous system, which makes no assumptions at all. It's unpredictable, but it's a much more accurate model of messy, real-world networks, like the internet.
The other fundamental models are just as important. The failure model defines precisely how components can break, from a simple fail-stop crash where a component just stops working, to these really complex Byzantine failures where it starts sending out corrupt data. Defining these possibilities is the absolute foundation for building fault-tolerant systems. And similarly, the security model defines what an attacker is capable of, which allows architects to design systems with strong defenses against specific threats.
So we've gone from the city plan to the building plan all the way down to the laws of physics. But why does any of this abstract modeling stuff actually matter in the real world?
Well, it matters because these aren't just academic exercises. Every single time you stream a video, make a bank transaction, or search the web, you are interacting with systems built on these very blueprints. Understanding them is really understanding the invisible architecture that holds our entire modern digital society together. They are the reason it all just works. And that leaves us with a final thought. These models have evolved over decades, from simple mini-computer networks to the incredibly complex, event-driven, asynchronous systems we rely on today. So as our world gets even more connected and the demands on our systems grow exponentially, you have to wonder, what brilliant new blueprint is just around the corner?